Today I take up a question of dry docking from the MV Hindship series, and this is part of the advanced ship stability problems. I hope you have been watching my previous videos on ship stability. I have about nearly 60 videos I think on ship stability. The links to those videos are in the description section below. Make sure you watch all those videos before you watch this video. I have previously addressed dry docking problems as well and explained a certain important and essential parameters that are involved in the dry docking calculations. So make sure you understand that as well. I'll address them again in this video, but still watch those videos before you watch this video on dry docking calculations. So let's get started. This is going to be a bit of a lengthy video. So if you're getting bored somewhere in the middle, just pause the video and then watch it later when you're ready for it again. Otherwise watch it at one go, but this is a long calculation. There is a lot of things involved in this problem, so you need to be a bit patient or watch it in parts. I leave it up to you. So let's get started with the question. Like I said, the topic is dry docking and it is from the MV Hindship series. It's an example from the MV Hindship booklet. So the question here is that the vessel MV Hindship is at a draft of forward draft 3.82 meters and aft draft is 5.46 meters. The vessel is in water of density 1.015, and this is important because the information provided in the hydrostatic tables of MV Hindship is for a water density of 1.025, that is the seawater density. So this is something you should note down at the very beginning. The vessel is being dry docked, of course, because we are doing a dry docking problem. The kg of the vessel, that is the distance from the keel to the center of gravity of the vessel, is 8.38 meters and the free surface correction is 0.12 meters. Assuming that the km, the mctc, the lcf and free surface correction remain unchanged over the range of drafts involved, calculate three things. Firstly, you have to calculate the virtual GM of the vessel on taking blocks all over. I'll tell you why virtual is important or why you have to note down the keyword virtual here. Then the second one is the vessel's righting moment at an angle of heel of 2 degrees at the critical instant. Alright. And thirdly, you have to find the vessel's fore and aft drafts at which her virtual GM becomes nil. Now we keep mentioning the word virtual GM or the loss of virtual GM. That's because before you start the problem, you have to visualize what may be happening here on the ship. So when the ship is trying to be dry docked and it initially comes into the dry dock, it comes with the initial trim, of course, right? And as soon as the vessel touches the block, now initially when the vessel comes into the dry dock, there is water there, because of which the underwater volume of the vessel provides the required buoyancy for the vessel to be able to float. Now as soon as the vessel touches, a part of the vessel touches the keel block, it could be, normally it's the stern part of the vessel, but again depends on the kind of vessel it is on, or the trim or the draft of the vessel, or what are the particulars of the dry dock. But as soon as a part of the vessel touches the dry dock blocks, there is a reaction or a force that acts upwards from here. This force is called P. Alright. So when a ship is floating, the weight of the ship is balanced by the buoyancy provided by the underwater volume. So what is the underwater volume? It is the volume of the vessel under the water. So this is the underwater volume of the vessel. This is providing the buoyancy. Now this would be so even at the instant when one of the end of the ship is just touching the block. So if the water level falls after the vessel touches the block, and part of the vessel has touched the block, remember that, not the entire vessel has sat on the block, right? Alright, so the entire vessel has not sat on the block. It's only a part of the vessel that has sat on the block. Alright, so here, even if the water level falls after that, the weight of the ship is resting on the block, while the remainder is supported by the buoyancy provided by the reduced underwater volume. Thus, at any instant, the total weight of the vessel is balanced by the upward reaction from the block, that is the force P, and the buoyancy being provided by the reduced underwater volume. Now at this instant you have to remember that as soon as a part of the vessel touches the block, part of the weight gets transferred to the block, and that is why an equal and opposing force reacts upwards. Now that part of the weight, whatever part of the weight is taken by the blocks, we assume that the vessel's displacement is reduced by that much amount, and we call it W minus P. But actually the vessel's displacement is not reduced, and that's why we call it a virtual loss of vessel's displacement, that is the weight of the ship. Similarly, when the part of the vessel touches the block, the part of the weight of the vessel gets transferred to the block. It is also equal to a discharging operation, as if a cargo has got discharged. And that is why we again assume that there is a virtual loss of the vessel's displacement, and we call it W minus P, where W is the original displacement and P is the force that acts on it, but that force is equal to the weight of the vessel that has got transferred to the block. Also, because it's equal to a discharging operation, as soon as a discharging operation takes place, the center of the gravity moves in a direction opposite from where the discharging has taken place. So if I say that the discharging has taken place from here, or assume, this is all virtual, there is no actual discharge, the center of the gravity also moves upwards. Right? So when the center of the gravity moves upwards, and if you have been studying my ship stability books, or rather my videos, you will know, sorry about that, you will know that here is the meta center, here could be the buoyancy, this is the center of gravity. Now as soon as the center of gravity shifts upwards, the GM of the vessel, which determines the stability of the vessel, reduces. And that is why we call it a virtual loss of GM, because actually the weight of the vessel has not reduced. There has been no discharging operation. But because that as soon as a part of the vessel touches the block, it feels as if a weight of the vessel has got transferred to the block and a discharging operation has taken place, and the center of gravity shifts upwards, leading to a reduction in the GM. So we call it a virtual loss of GM. So this is the basic theory that you have to know behind it, and then I'll show you the calculations on how to go about it. So if you see here, you have been given the forward draft and the aft draft, which is 3.82 meters and 5.46 meters. Now first thing you do is you calculate the trim. The trim is always calculated by subtracting the larger draft, rather the smaller draft from the larger draft. So you get 1.64 meters, because 1.64 is equal to 5.46 minus 3.82. So I have subtracted the forward draft from the aft draft. Now because the aft draft is more, we say the trim is by stern. The vessel is trimmed by stern, 1.64 meters. And then you calculate the mean draft, denoted by M. This is the mean draft. How do you calculate mean draft? You take the forward draft and the aft draft, add it, divide it by 2, and you will get the mean draft. Mean draft is 4.64 meters. Now we need the mean draft to calculate the hydrostatic draft. That is the draft we are after. But because we don't have the information here, we'll calculate the hydrostatic draft from the mean draft. So how do you do that? Once you calculate the mean draft, you have to go into the hydrostatic tables for MV Hindship. Now even if you are sailing on the vessel, your vessel will have a hydrostatic particulars booklet. Also, the same thing is loaded in your loadicator. So for a mean draft of 4.64 meters, we will go into the hydrostatic tables. So when I go into the hydrostatic tables here, you can see that the draft of 4.64, which is the mean draft, is not given here. What is given here in the draft column is 4.6 and 4.8. There is no 4.64. 4.64 will be lying between 4.6 and 4.8. Right? So for 4.64, if I have to calculate the LCF, LCF is the distance of the center of flotation from the aft perpendicular. So if I have to calculate the LCF for a mean draft of 4.64, I will take down the values of 4.6 and 4.8, LCF values for 4.6 and 4.8, and then do the necessary interpolation to calculate the LCF value for the mean draft of 4.64. So why do we need that? Because we are trying to get to the hydrostatic draft, and I'll show you how we do that. So basically I noted down the LCF values for the drafts of 4.6 and 4.8 from the hydrostatic tables. But because I need it for a mean draft of 4.64, I will be doing some interpolation. So you can see the interpolation is shown here. For a difference of drafts of 0.20 meters, which is the difference between 4.8 and 4.6, the difference of LCF is 0.043, which is the difference of the LCF values for the draft of 4.6 and 4.6 and 4.8. Right? These are the LCF values. But I need it for 4.64, so for a difference of 0.04. What is 0.04? 0.04 is the difference between 4.64 and 4.6. So for a difference of 0.04, what will be the difference in the LCF value? So we will do a cross multiplication. Alright, so if you didn't get this interpolation, watch how I have been doing it. So I have told you that for a difference of 0.20, that is the difference of draft between 4.8 and 4.6, the difference in the LCF values is 0.043. So for a difference of draft of 0.04 meters, which is the difference between 4.64 and 4.6, the required mean draft and the given hydrostatic draft, the LCF correction value can be found by cross multiplication. So if I do a cross multiplication, I get a correction value or LCF correction value of 0.0086. Now I can see as my draft is increasing from 4.6 to 4.8, the draft is increasing, the LCF value is going down. Right? So when I go from 4.6 to 4.64, the draft is increasing, the LCF value should be going down. So what I'll do is I'll take this correction value and subtract it from the LCF value of 4.6 meters of draft to get the LCF for 4.64 meters. Because the LCF for 4.64 should be less than what it was for 4.6, because I can see as the draft is increasing, the LCF value is going down. So the LCF value we get for a mean draft of 4.64 is 73.0084. Now using this LCF value, the trim that we calculated before and the length between perpendicular in the denominator, I can find out the correction that I can apply to the aft draft to get my hydrostatic draft. Now I calculated above, I showed you already, it was 1.64. The LCF I have just calculated. Now where did I get my LBP from? My length between perpendicular. I'll go back to my hydrostatic tables, and in the hydrostatic tables, in the initial first pages or so, you have your LBP given to you. Your LBP is nothing but length between perpendiculars, and you have calculating everything in meters, so you will take the meters value of 143.16, go back, put it here, and you will get your LBP value. So the correction you get to the aft draft is 0.836 meters. This is the correction that you will apply to the aft draft. So the aft draft is 5.46 meters given to you in the question. Aft draft correction is always negative. You will always subtract it, especially when the vessel is trimmed by stern. Subtract the correction from the aft draft and you get your hydrostatic draft. This is your hydrostatic draft, 4.624 meters. Alright. So now you've got your hydrostatic draft. What you have to do is basically obtain certain parameters from the hydrostatic tables. But those parameters will be for a water density of 1.025. Alright, this is for 1.025 density. Your vessel is in water of density 1.015. So you need to obtain those values from the hydrostatic tables and then again make some changes to it or corrections to it or interpolate it to get the value for the right density in which your vessel is floating. Alright, So for a hydrostatic draft of 4.624 meters, you go back to the tables, and because you will not have the draft of 4.624 meters, you again do what you did before. You will note down the values for a draft of 4.6 and 4.8, and we will do an interpolation as we did before for the values of displacement denoted by this triangle, MCTC, which is moment to change trim by 1 centimeter, LCF, which is the longitudinal center of flotation or the distance of the center of flotation from the aft perpendicular, and the Km. What is Km? Km is the vertical distance from the keel of the vessel to the meta center. Alright, so what we do is we go back to the tables, and here again I go back to the same place, 4.6 and 4.8, and again I will note down the LCF values, but this time I will also note down the displacement values, the MCTC values, and the Km values for 4.6 and 4.8. After I note down these values, I have written them here. I need to interpolate it for the hydrostatic draft of 4.624 meters. You remember how we did the interpolation? So I'll show you all the interpolations, and if you don't get it at one time, then watch this video again to understand it. So the interpolation is always simple. For a difference of draft of 0.20 meters, that is the difference between 4.8 and 4.6, the difference of the displacement is 438. 438 is 9348 minus 8910. Therefore, for a difference of draft of 0.024, which is nothing but 4.624 minus 4.6. So 4.624 is the hydrostatic draft that we want the values for. What will be the difference in the displacement? And we will do the same for the MCTC value, the LCF value, and the Km value. So this MCTC value is again a difference between 165.4 minus 163.8. So we will do an interpolation from here, and I'll show that to you. So I don't want to confuse you right now. Let me address it one by one. Otherwise you guys will get confused. So let's solve the displacement problem first. So once you do a cross multiplication, it's 0.024 multiplied by 438 divided by 0.2. You get a correction of displacement value of 52.56. Now as you can see above, as the draft is increasing, displacement also is increasing. So that means from 4.6, when we go to 4.624, our displacement should be increasing. So I will take this correction value, I will add it to the displacement of 4.6 meters, which was 8.908910, and when I add it, I get my displacement for 4.624 meters. This is my displacement for 4.624 meters. But remember, this is for a density of 1.025, because the tables, the values in the tables are given for a density of 1.025. Let me show you. When you go into the tables, you can see above here, it mentions here that these values are for specific gravity 1.025, which is the salt water density. So we'll have to apply some corrections to convert the displacement value for a density of 1.015, where the vessel is floating. Right? So I'll show that to you later. Let me show you the interpolations first. So like I said before, that whatever you did for displacement, you have to do the same process for the MCTC as well. So here you will do a cross multiplication like this, which results in this cross multiplication. Again, when the draft value is increasing, the MCTC value is increasing. So when you find the correction, you will add to the MCTC of 4.60 meters draft, which was 163.8. When you add it, you get the MCTC for a draft of 4.624, and again this is for 1.025 density. When you have done it for MCTC, you will do the same thing for LCF. Again, this is the difference between 73.017. Again, always take the smaller number and subtract it from the larger number. Don't make these number values negative. You can make it negative, but basically you must see the pattern here. So this time you can see that as the draft is increasing, the LCF value is decreasing. So you can, whatever correction you get, you should be subtracting it from the draft of 4.6. You have to reduce the LCF for 4.624. So whenever you do a cross multiplication, again its results here. So this time when you get the correction, you will subtract it from the LCF value of 4.6 meters. And then this is the LCF value for a draft of 4.624, but again for a density of 1.025. Right? And finally, this is the interpolation for the Km. So Km is the same procedure, Km here, here. This is nothing but difference between 9.196 minus 9.032. Again, you can see as the draft is increasing, Km is decreasing. Therefore, as you go from a draft of 4.6 to 4.624, your Km value should be decreasing. So this interpolation is shown here. So you can see here the Km value correction. As soon as we get this here, I will subtract it from the Km value of 4.60. This is a Km value for 4.60 draft. You will reduce it and you get the Km value for draft of 4.624, but for a relative density of 1.025. Alright. Now, you have obtained the values of displacement, MCTC, LCF and Km for a hydrostatic draft of 4.624, but for a relative density of 1.025. Right? Now, you need these values for a relative density of 1.015 because that is the density in which the vessel is floating. But the key thing you have to remember here is you only need to interpolate the values for displacement, denoted by the triangle, and MCTC. Alright? You don't need to do it for Km values and LCF values. Why? Any values which are in meters holds good for all densities. So Km value and LCF value, they are all in meters. So if you have calculated those values for a relative density of 1.025, the same value holds for all other density, including density of 1.015. Any other value which is not in meters, such as displacement, MCTC, then you have to convert that for a relative density of 1.015. So therefore, I will only convert the displacement and MCTC values for the density of 1.015. So the displacement that you calculated for a draft of 4.624 was 8962.56, but it was for relative density 1.025 seawater density, but I need it for the dock water density of 1.015. So I will again do a cross multiplication. When I do a cross multiplication, I get the displacement 8875.1 tons, and this is for a relative density of 1.015 in which my vessel is floating. Similarly, for MCTC, I will do the same thing. The MCTC you calculated for a draft of 4.624 was 163.992, but that one was for seawater density. I need it for a dock water density. I will do a cross multiplication, and that will give me a MCTC value of 162.392 meters for a dock water density of 1.015. The LCF and the Km values, which are in meters, will remain the same as you calculated before. So the Km value will be 9.17632. It will hold good for that density, and the LCF value will be 73.01184. It will not require any kind of interpolation for change in density. So the Km value, as you calculated above, was 9.176 meters. Kg was given to you in the question, So you will subtract Kg from Km and you will get Gm solid. So Kg is always subtracted from Km to get Gm. Gm solid means GMS is Gm solid. Alright, this is Gm solid. That means the free surface correction has not been taken into account. So you will subtract the free surface correction, which is as a result of unfilled compartments, unfilled tanks rather, liquid tanks. And once you subtract, it is always subtracted, you will get the GM fluid. This is GM fluid. This is the corrected GM. This is the GM of the vessel when the vessel is entering the docks. Now the virtual loss of GM on taking the blocks all over, when the vessel is sitting on the blocks all over, when the entire vessel is sitting, is calculated by P, which is the upward force, remember I explained that before, multiplied by small a. This small a is nothing but the distance of the center of flotation from the aft perpendicular, basically the LCF. This equals trim, or this is the trim that we have known before, multiplied by MCTC, the one that we calculated before. So in this, we know the MCTC, we know the trim, and we also know the LCF. So what I'll do is I just need to calculate P. P is the upward force that acts on the vessel as soon as the vessel touches the block, right? The P force acts upwards, equal to the weight of the vessel taken by the block. So that can be calculated when you bring A here, because P is the unknown, rest of them are knowns. Put the values of the trim as 164. Now remember, the trim we calculated was 1.64 meters. You need to convert it into centimeters. So 1.64 meter multiplied by 100 will give you 164 centimeters. Now why are we taking centimeters here? You may ask me. Because the moment to change trim by 1 centimeter, MCTC, is in centimeters. Right? So the trim also has to be in centimeters. It cannot be in meters. Alright, and then we divide it by LCF, which is 73.012 as you calculated above. And then when you do the division, you get the answer of P, 364.766. That is the P. So if you just calculated 164 multiplied by 162.392 divided by 73.012, you will get 364.766. You may get up to more decimal places, but we round it off. It's up to you how much you round it off to. You can go more if you want to. Alright. Now once we got the P value, we can start calculating the first part of the question. The first part of the question required us to calculate the virtual GM on taking the blocks all over. That means, what was the virtual GM? That means because we assume that there is a virtual loss of GM, right? Because as soon as the vessel touches the block, we assume a discharging operation has taken place, because a part of that vessel's weight gets transferred to the block. And that's why as a result, the center of gravity moves upwards, the GM is reduced. So we call it the virtual GM. You know, once the GM is reduced, whatever is the GM, we call it the virtual GM, because the loss of the GM is virtual, it's not real. So when the vessel takes the blocks all over, when the entire vessel is sitting on the block, you can calculate the virtual GM by two methods. So the first method is virtual loss of GM equals P multiplied by kg divided by W minus P. W minus P because, like I told you before, as soon as the part of the weight gets transferred, we may assume that the vessel has lost its displacement, like a discharging operation. Although it has not, but here, because it's an apparent thing, it's a virtual thing, the first method we assume that there has been a loss of displacement, like a discharging operation. So P that we calculated before, above you can see 364.766 has been written as 364.8. Doesn't matter if you want to write it at 364.766, you can write this. This has come from here. I've just rounded it off. Multiplied by 8.38, this is the kg given to us in the question, divided by the displacement that you calculated for the relative density of 1.015 above, minus the P value again, 364.8. This is again the P value that you calculated above, right? The virtual loss of GM that you get is 0.359 meters when the vessel is sitting on the blocks all over. But the original GM when the vessel was entering the blocks or entering the dry dock, we calculated above, was 0.676 meters, right? That was the original GM that we calculated above, after we subtracted GM solid from, or free surface correction from GM solid. So virtual loss of GM comes here, is a loss, so you will subtract it, and the virtual GM you get is 0.317 meters. That's the first answer. That is the virtual GM after the vessel loses apparent GM, and this is the final GM after the vessel takes the block. In method 2, we want to calculate the same thing. We want to calculate the virtual loss of GM, but here we are assuming that the vessel has not lost any weight, because actually when the vessel is sitting on the blocks, it actually has not lost any weight. it is only a virtual loss of weight. So here we assume that the vessel's weight or vessel's displacement remains the same. It remains unchanged. So the formula becomes P multiplied by Km. So here we assume there is no shift in the center of gravity as well, because if there has been no loss of weight, the center of gravity will not shift. The center of gravity shifts only if there is a loss of weight or an addition of weight, right? So here, because we are assuming there has been no loss of weight of the ship, the vessel's displacement remains unchanged. I'll write that here. And because displacement remains unchanged, center of gravity has no role to play, it has not gone up and down, we take Km for no change in center of gravity. So we take the Km value. So therefore this formula is P, as you calculated above, multiplied by Km, also that you calculated above, 9.176 for a hydrostatic draft of 4.624 meters and relative density 1.015, and of course the displacement again for that we calculated above for a relative density of 1.015. Now remember, take the values that you calculated for the relative density of 1.015, because that is the water in which your vessel is floating. You cannot take the values for the relative density of 1.025 because that would be incorrect. So don't get confused. Make sure you highlight those values that you need to use in the rest of the question. Otherwise your question is wrong. You will lose marks for it. Alright, I can't stress that enough. So once you do that, you get a virtual loss of GM of 0.377. Virtual loss means loss, that will be negative. Your original GM that you calculated above was 0.676 meters. A virtual loss when the vessel sits all over, but there has been no loss in the displacement, and hence the virtual GM is 0.299 meters in this case when we assume that there has been no loss. So you can see the difference is a slight difference is there, only 0.018 difference is there. It's not much of a difference in the GM values when the vessel is sitting all over, whether you assume there is a loss of weight or whether you assume the vessel has not lost weight. The important thing here to remember is throughout the period when the vessel enters the blocks, it touches the block for the first time, so a part of the vessel is touching the block till the time it sits all over. So the time it just touches the block, the first part of the vessel touches the block is called critical instance, and till the time the entire vessel sits on the block is called critical period. So during all this time your vessel should be stable. Alright, because as soon as the vessel touches the block, there could be a slight heel that will develop. So a slight heel might develop, but if your GM is not adequate, if your stability is not adequate, the vessel may topple over. It is a dangerous situation. So that is why you need to calculate your GM when the vessel before entering the dry docks and after the vessel takes the dry dock, or also throughout the period, to ensure that the vessel is stable throughout. That is your aim as a chief officer. So the second thing we'll calculate will be the righting moment at angle of heel of 2 degrees at critical instance. So like I said, as soon as a part of the vessel touches the block, a vessel might develop a heel. That heel could be big or small. So if it is small, of course, if the GM is adequate, righting moment is nothing but a moment that brings back the vessel to a upright condition. Right? So that is why if your GM is adequate, you will have the adequate. So let me show you again. I have discussed all this before and I hope you have been watching those videos, but just in case if you have not been watching the videos, then I'll just quickly discuss this because you may have forgotten this concept here. So I'll show you what happens here. So let's say a vessel develops a list or a heel rather. And what happens here is that the center of the gravity may shift. And this is the meta center and this goes up here. This is the keel. So what is happening here is that the center of the gravity may shift. But in some cases what happens is when the vessel develops excessive list, and I'll show that to you as well. So vessel has developed excessive list, the center of the gravity may shift and cross over on this side. So this is this portion here becomes the righting moment, which brings back the vessel to the upright condition. Alright, so that is the righting moment of the vessel. So anyhow, I didn't have enough space to draw the diagram, that's why I was not drawing the diagram correctly. Anyhow, we have discussed all this before, so make sure you watch those videos. So righting moment can be calculated by two methods as well. In method 1, righting moment or RM equals GM sine theta W minus P. Again here we have assumed that there has been a loss in the displacement of the vessel, and GM has been taken as the GM after it has been reduced by a virtual loss. So GM is not the GM that you calculated earlier. This GM is after the vessel has lost a virtual loss of GM has taken place. So GM multiplied by sine theta. Theta is nothing but the angle of heel, 2 degrees. So sine 2 degrees multiplied by the displacement minus the P, force P that you have done before. Here you get the writing moment as 94.1 tons meter. Method 2, writing moment, again you will assume that there has been no loss of displacement. In the earlier example, method 1, you are assuming loss of displacement. GM multiplied by sine theta, again sine theta is angle of heel, multiplied by unchanged displacement. So unchanged displacement is 8875.1, sine theta is sine 2 degrees, and GM is 0.299. Where are we getting these GM values? Remember, these are the GM values. This is from method 2, this GM value after a virtual loss has taken place. Alright, and here in method 1, it's this GM here that you have to take. That's the GM that you have to take. Alright, so you get the value of 92.6 writing moment tons meter. So 92.6 is not too far from 94.1, it's pretty close. So 94.1 and 92.6 meters is the writing moment. Finally, the third part of the question is you have to calculate the forward and aft drafts at which her virtual GM becomes nil. Now for virtual GM to become 0 or nil, virtual loss of GM must equal to the original GM. So when you were entering the dry docks, you had an original GM, right? So the original GM, if it has to become 0, if the virtual GM has to become nil, that means the original GM has to equal to the virtual loss of GM. So then your GM will become 0, right? So the drafts at which her virtual GM becomes nil, method 1, again virtual loss of GM will be equal to P multiplied by kg divided by W minus P. So again, because we assume that an apparent loss of displacement has taken place, we also take into account the center of gravity or a shift in the center of gravity or a change in the kg, and therefore we take P multiplied by kg divided by W minus P. Here you know kg, you know virtual loss of GM is equal to nothing but the original GM that you calculated above. Original GM becomes 0.676, right? So here you will take this here. So 0.676 multiplied by W minus P will be equal to 8.38 by P. Put in the values there, go step by step, transfer this here, this becomes addition. So finally P, the new P that you calculated when the vessel takes the blocks all over, will be equal to 662.5 tons. So of course this will be more when part of the vessel has just touched the block. This is the P when the entire vessel is sitting on the block. So for virtual displacement, when GM becomes 0, will be equal to a loss of the vessel's displacement will take place. So the original displacement that you calculated 8875.1 minus P, the revised P when the vessel takes the blocks all over. And this is the virtual displacement 8212.6, because we are assuming that displacement has been lost here. The equivalent displacement in seawater will be, this is in dock water, 1.015. So the equivalent displacement in seawater will be cross multiplication. So you will do 8212.6 multiplied by 1.025 divided by 1.015. Why you are doing this? Because you need to use this displacement to enter the hydrostatic tables to find out your hydrostatic draft once the vessel has sat on the blocks all over. So you will take this displacement, go into the tables. So for 8293.5, so when you go into the tables, you can see that there is no 8293.5. What you have is 8038 and 8473. So 8293.5 will lie between here. For this displacement, you have to find the hydrostatic draft. That's why you have to convert the displacement from the displacement of 1.015 to the displacement of 1.025. So when you go there, you have these two displacement values, but you need it for this displacement value. So of course you do the interpolation as you did before. For a difference of drafts of 0.20, the displacement difference is 435. How did I get 435? You can see here 8473 minus 8038 and 4.4 minus 4.2. So for a difference of displacement of 255.5, which is the difference between 8293.5 and 8038, what will be the change in this draft? So the change in the draft will be 0.117 that you will add to the hydrostatic draft of 4.20, because you can see as the displacement is increasing, the draft is also increasing. So we need the draft value for a displacement value of 8293.5. So you will add the correction value to the hydrostatic draft of 4.2 and you get the hydrostatic draft of 4.317 when the vessel is already on level blocks. So when the vessel is already on level blocks, here the hydrostatic draft will be equal to the drafts forward and aft. Right? The water level will be the same forward and aft, because there is no concept of the weight acting. The entire weight of the vessel is now resting on the blocks. So the forward and aft drafts will also become equal to the hydrostatic draft. Similarly, we'll use method 2 to calculate the drafts again. And again here we assume that there is no loss of displacement. So virtual loss of GM equals P multiplied by Km divided by W. For virtual GM to become 0 again, virtual loss of GM must equal the original GM. So virtual loss of GM becomes equal to original GM here, right? Which is equal to P multiplied by 9.176, that is the Km, multiplied by divided by the unchanged displacement of 8875.1. So you find out the value of P by cross multiplication and you get P as 653.8. So here virtual displacement when GM becomes 0 is 8875.1 minus P, which gives you a displacement of 8221.3 when the vessel is sitting on the blocks all over. Again, you convert this displacement for a displacement of seawater displacement, because you need to enter the hydrostatic tables again to find the hydrostatic draft. So this displacement when the vessel is sitting on the blocks is for water of density 1.015. You will convert it for 1.025 by multiplying it by 1.025 and dividing it by 1.015. You get the revised displacement. Again, you take this revised displacement of 8302.3, 830.23, 8302.3 also lies between the same displacement of 8038 and 8473. So the process is the same. You will go back, write down the values. So for a draft of 4.2 it's 8038, for a draft of 4.4 it's 8473, but you need it for a displacement of 8302.3. So as we have done before, you will do an interpolation. I have shown you the values of interpolation. Hopefully you don't need to understand it again. The video is becoming unnecessarily long, not unnecessary, but it's becoming quite lengthy. So you do a cross multiplication, you get the correction value for the draft. So as your hydrostatic draft, or as your displacement has increased, your hydrostatic draft should be increasing. So you will take this correction value and add it to the hydrostatic draft here. And you will get the final hydrostatic draft 4.321 meters. And again, when the vessel is already on the level blocks, the hydrostatic draft will be equal to the drafts forward and aft, because the entire weight of the vessel is being taken by the blocks. The distribution of weights on the ship will not matter then. And therefore, the final hydrostatic draft is 4.321 meters by method 2. So I know guys, this was a very long solution, a very long question. There's nothing I could do about it. These dry dock problems are very long. I'll take up more problems in the future from MV Hindship book, because there's a lot of calculations involved, a lot of parameters. You have to go backwards and forwards into the hydrostatic tables. But I hope you understood the question. If there are any doubts, just write it in the comment section and I'll be trying my best to answer the questions. I get a lot of queries in a day. I try my best to answer all of them. But let me know what you thought about this video, whether you liked it or not. And I'll see you soon with my next video, guys. All the best for your studies and bye for now.